Hey guys, welcome back to AP Physics C, Electricity and Magnetism. My name is Kristen Gonzalez Vega, and I am in my house here in Frisco, Texas. I have Roger with me over in Florida. Hi, Roger.
Hey everybody, my name is Roger Siegel. I'm coming to you from Sarasota, Florida.
Okay, so tonight we are going to talk about more circuits. We are going to do some, I'm going to talk a little bit about the test first, but we are going to do some, oops, let me get back to the beginning here. We're going to do some circuits with resistors, but we're going to add in capacitors today because we have done lots of just resistors, and I think it's time for us to start putting in some capacitors. But we're only going to do steady state capacitors today. Tomorrow, we will go into some non-steady state capacitors and what happens while they are charging or discharging. So I wanted to go over some of the updates that you can find about the exam this year. And there's a YouTube on the AP YouTube channel, not the review channel that you're looking at here, but on their main channel, they have some videos explaining that, but they're also on the main page. So a good website for you guys to go to and bookmark is www.cb.org/AP2020. And that has a ton of stuff on there. So let me switch my share over here so I can show you what some of that stuff is on there. Okay, so if we look at the page, you can see here there is a link for this schedule of the exam. So you can look and see again when all of those tests are going to be. And you can see that ours is going to be on May 11th, depending on where you are, different times, following the mechanics exam. So if you're taking both, you have a little bit over an hour in between, but they are back to back essentially. And also, if you keep scrolling down and you go to the specific course information, that's where you can actually find the more detailed details of the exam. So you can see our 2 questions, what those are going to be like, that we've got one that's similar to those qualitative, quantitative questions from Physics 1. If you guys took that last year, that's that kind of what's happening in the situation, just touchy-feely, and then maybe a little bit of mathy, but kind of going back and forth between those 2. And then there's also going to be a lab-based question. So the split is a 60-40 as far as the percentage of the exam. You're going to have some time to work and some time to upload, but they are not going to be separate. So you need to be keeping track of those 25 and 15 minutes on your watch so that you don't run out of time before you upload. You get to choose how you upload, whether you're going to do that by typing into a Word, a Google Doc, and like copy paste. I think that might be a good way to go, or you can handwrite and upload a picture of your writing. If we go back, there is also, if you go in to learn more about taking the exams, it has all those details about the exam itself. So some tips there for taking open note, open book exams. Please don't count on those notes, right? So you need to prepare, just like you didn't have notes. If you have a sheet that has a couple of little things, I think you should not focus on making a 5-page cheat sheet. You're going to waste too much time going through that, and you will not have time to answer the questions. Prepare for the exam as if it was not open note and rely on what you know rather than what you can find, okay? The exam timing you can see is on there too. Everybody's taking it at the exact time. There's some getting ready tips on there. There is a checklist for what to do to make sure you are prepared for the exam. There is also, let's see, where is it? Going to be May 4th, where you can log in and put in your ID and practice uploading something to the website in that format that they're going to have. So there's some good things for you guys to look at. And let's look back here at our PowerPoint. Okay, so today we're going to be looking back again using Kirchhoff's loop and junction rule to solve for multi-loop circuits, finding current, resistance, potential difference in a circuit. We're also going to look at some capacitors in our circuits. Again, only today will be steady state. We will add in some non-steady state charging and discharging tomorrow. And on Friday, finish it up. And then Friday will be done. Next week, we are going to be doing some practice test problems. So Monday will be kind of like a mock exam where we will give you a couple of problems. Roger's going to proctor you through that. And then we are going to go over those problems on Tuesday. And then Wednesday, we are going to do that same thing again. I'm going to proctor you for a couple of questions. Thursday, we're going to go over them. And then Friday, we're going to have one last kind of hurrah to celebrate our hard work that we've been doing these past few weeks and to just give you some last minute tips and tricks. So let's get into it. Switch over here so I can draw. Let's review what these loop rules are really quick and junction rules are for Kirchhoff's rules. Our loop rule, remember, which was based on conservation of energy, is that if you go any one loop around your circuit, your potential gain should equal your potential drops. And our junction rule is that for any junction in your circuit, the amount of current going into that junction should equal the current out. Okay. If you're not really familiar with those, you might want to watch our past 2 videos because that's where we really kind of dug into those and looked at those specifically. Okay. So we're going to add in capacitors today too. We talked about these a little bit before with capacitance and how they behave. But again, as a reminder, when we have capacitors in a circuit, when they are uncharged and we flip a switch, initially at that time equals 0, those capacitors are going to act like a wire or like a closed switch. After a long time, when they are fully charged, they're going to act like an open switch or in some cases a short circuit. Okay. So let's look here. Today, I also want to go over, well, what happens if you have 2 batteries in a circuit? So let's look at the circuit we have here. I have a 6-volt battery on the left and a 6-volt battery on the right. I've got 1, 2, 3 resistors in my circuit, and I'm actually even given the directions of the currents. You won't always be given the directions, but in this case, we have the directions of those currents, right? So we can look at either one of these junctions, we can draw loops and look around, but here's how you want to approach these. So I have kind of a list of some steps to do. The first thing I always do is I identify what I think my loops are. Sometimes there can be more than 2 loops, but really you just need to make sure that you are identifying loops so that every resistor is somehow included in a loop. So you can just do 2 loops, even if there could be a possibility of 3, as long as every resistor is included in a loop, then you're going to be good, right? So let's do that. If I start with this 6-volt battery on the left, I can follow it around. Remember, we go out positive, around. I could get to this junction and go down around here. So I'm going to call that loop 1. I could look at my 6-volt battery on the right, starting at that battery, going up, and also go down through here and back around. I'm going to call that loop 2. If you wanted, you could choose the outside loop, but for some reasons we won't go into, that might not be as useful, right? But it doesn't matter. You can pick any loop you want as long as you've got loops for all of your resistors. Okay. The second thing you want to do is write equations using your loop rule for those loops. Okay, so let's go around. So remember, potential gains have to equal our potential drops. So as I go around, as long as I'm going out the positive end of the battery, then that's a positive gain of potential, right? So I'm going to say I got my, let's just write it without anything in first, right? So I've got the EMF of the battery. Since I'm going from negative out positive, that's a positive. I'm going across my resistor here. And so that's going to be a potential drop across here. So we're going to say minus that potential difference across. Let's just call this resistor 1, resistor 2, and resistor 3. So there's a potential difference drop across resistor 1, right? As I keep going down through here, I've got another drop here. So minus the potential difference through resistor 2. And then I get back here, that should equal 0. So we can then actually plug in that this is a 6 volts minus, well, how would I find what that potential difference drop is across my resistor? We use Ohm's law, and it's the current times the resistance. So here's where, if it's not already identified, you want to identify your currents. So they're already giving it to us here that the current is up here, down here, up here. So if we go around and the current's traveling through here, well, we can say that this is I1 times 150. Okay, and I keep going down through that middle branch. That's another potential difference drop across there. And that's we're calling current 2, right? It is not the same current, because if we look at our junction rule, well, we've got current going into our junction here. We've got current going into our junction here and going out here. So we can't call those the same currents. They're different currents. So if you're not given labels, you want to make sure that you're creating your own. Okay, but we're given it here. So this is going to be minus 200 times I2, which should equal 0. Okay, so let's do that for loop 2 also. I guess this really kind of should have been in blue, but let's look at loop 2. So this is loop 1. And I'm going to go ahead and just start plugging in numbers because we're kind of all familiar with this now, right? So as we go through, we're going out our battery, out that positive. So that's a positive 6. We got a potential difference drop across our 100 ohm resistor. This is now current 3. Let me erase this so we can see. Okay, so that's current 3. So we're going to say this, and this is 100 ohms. So this is minus 100 times I3. Whoops. Okay, we go down through that middle again, minus that 200 times, it's still I2, and that equals 0. Okay, so you pick your loops, you write your loop rule around. Okay, the next thing is we have to write our junction rules, because this isn't enough to solve for the currents, right? Because I got an unknown current I1, an unknown current I2. I got 2 unknowns, so we know we can't solve just with that. But we can add in our junction rule. And so if we look at the junction here, well, I've got I1 going in, I've got I3 going in, and I've got I2 going out. So if we write our junction rule, we know that I2 is equal to I1 plus I3. Right? You could write it the other way around, doesn't matter. But we know that current that's going down through that middle resistor is a combination of those 2 currents going into that junction. So that's what we do next. We write our junction equation. We've written our loop rules, we made our loops. So now we have 3 equations that have all these 3 unknowns in it. So how do we put these together? The way that I see is the easiest is I'm going to use my junction rule, but I want to substitute in so that I have everything in terms of only 1 current. So let's make everything in terms of just I2. So I want to get rid of I1 and I want to get rid of I3. So I can get rid of I1 using our loop 1 equation. So let's rearrange it to solve for what I1 is equal to in terms of I2. So if I rearrange and I just want to solve for I1, well, let's add that over. So we've got 6 volts minus 200 I2 equals 150 I1. Okay, so then I1 will equal 0.04 minus 1.33 I2. Okay, so I could plug that in right here for I1, and look, I'm going to have I2, I2. We'll do that in a second. Now let's do the same thing with our equation using our loop 2. I want to get rid of which one this time? I want to get rid of I3. So let's solve for what I3 is. So we're going to say 6 minus 200 I2 equals 100 I3. And so if we divide out by 100, then we get that I3 is equal to 0.06 minus 2 I2. Okay, so now I've got what I3 really is equal to. I've got what I1 is really equal to, so I can plug those into my junction rule. Okay, so then we have I2 is equal to, well, I1 is 0.04 minus 1.33 I2 plus I3 is 0.06 minus 2 I2. So now I've got everything in terms of I2, so we can rearrange and solve for I2. We can combine our 0.04 with our 0.06. We can combine our 1.33 with our 2, and then bring those over, rearrange. What you get is that I2 is going to be equal to 0.0234 amps. Okay. And then I could plug that into these other ones and solve, because I have these equations for what I1 is, and I have what I3 is, but we're not going to do that just to save time. But those are your rules. Pick your loops, write your loop equations, write your junction equation, and then use that junction equation to substitute in what those other currents are so you can get what just one of them is. Okay. There was actually a question last year that had 2 batteries. So it's not often we see it, but once in a while, and you got to know how to do it. Okay, so Roger is going to go through a couple more practice problems with us. So
Okay.
Roger, take it away.
All right, thanks, Kristen. All right, well, let's take a look at some more problems to get us ready for this wonderful test that we have. And I'm going to come over to my OneNote here. Excuse me. And let's get ready here. Okay, great. Now, so we're continuing to look at circuits and current, and so let's see what we can find over here. In this next problem, we're going to do 2 different iterations of this. You can see that we start with a circuit, and our circuit's got we got a battery here on the left, 1500 volts, a switch. We've got a 200 ohm resistor, a 300 ohm resistor, a 100 ohm resistor, and then we've got a little gap here. All right, and so this is a wonderful tool for the teacher, because the teacher can say, okay, let's put some different things in that gap and see what happens. So that's what this question is asking. It says, in case 1, a student connects a 50 ohm resistor to points A and B. And in case 2, a student connects an 80 ohm resistor to points A and B. I'm sorry, an 80, did I say 80 ohm resistor? My goodness. Let me take that back. An 0.8 microfarad capacitor. It helps if you read it. Okay, so let's, and so it says compare the current through R1 in case 1 to the current through R1 in case 2 at t equals 0 when the switch is closed. So let's talk about this. So there's some important things about this. So it's been a while, but when we studied capacitors, let's talk about how they function. So when I have a capacitor that is uncharged and I put it in a circuit, it doesn't behave the same way all the time. And let's talk about why not. When I close the switch, charges, remember, we're going to map our charges out of the positive end of the battery. Charges start to get pushed here, and that pushes positive charges here, which then leaves negative charges here. But you can imagine that since there's no communication between these 2 plates of this, we don't have no charge can pass between the plates. There's this conductive barrier, this insulating barrier here, that this can't go on forever. And so, how can we think about this? Well, I asked my students to think about it this way. I said, imagine you've got a pipe, and in that pipe is a very flexible yet super strong membrane, okay? And so we've got this pipe, and it's flexible and strong, and there's water on both sides of the membrane, and the water's not moving, okay? Now, if I start to push the water from the left here by using some kind of pressure device, I can make this membrane stretch, and I can make it stretch a lot. Now, it's not going to break. Now, notice that as this membrane stretches, it pushes water away from it. And so when we first close a capacitor, it's like the membrane is in its relaxed position. And then when we turn on the juice, we start to get the membrane stretched more and more and more. Now, it can't stretch indefinitely, because the more it's stretched, the more force it pushes back. And so eventually it's going to be stretched to its maximum, and there won't be any flow anymore, and we'll have a new static situation. And that's what happens here in this circuit. When we start the circuit, when we throw the switch on this is current versus time. At the beginning, the current it acts as if there was nothing there, as if there was just a wire, not nothing, a wire. And so this is V over R. That's the initial current. And so it's very important when we're looking at capacitor problems that we look at what the time is. When is this happening? And so in this problem, you can see at t equals 0. All right, so we can figure this out. So at t equals 0, I'm either going to have a resistor here, or I'm going to have a capacitor here. Now, if I have a resistor, adding a resistor to another in series increases the resistance. Okay, and so we can figure out the resistance before with the capacitor. And remember, the capacitor provides no resistance. And so the resistance with the capacitor, effective resistance, is going to be this 200 plus these inverses. Remember, this is 300 inverse plus 100 inverse. And so this turns out to be 275 ohms. All right, and that's my total. Now that's my resistance in the whole circuit. Now, if I put a resistor in here, well, then I get 200 plus 300 inverse plus what? Well, if I put a 50 ohm resistor next to a 100 ohm resistor in series, that's going to give me 150. And so when I do that, I get 300 ohms. So the answer to the question, the current through R1 in the main branch, that's going to vary inversely with the resistance. The higher resistance, the less the current. So when we put the resistor in here, we have less current. So that means IR is less than IC with the capacitor. In this case, adding a resistor in series reduces the overall current in the circuit. Now let's look at the next iteration of this. This one's a little bit more complex, and we got to appreciate it for that. It says, compare the drop in voltage across R2 at t equals 0. Once again, all important when we're talking about capacitors. At t equals 0 to that after a long time in case 2 when the capacitor is attached. So let's go ahead and look at that. So we're going to have, we're going to put the capacitor on there, and we're going to say what happens at, what is the voltage drop across here at t equals 0, and what is the voltage at t as t goes to infinity, a long time. And that's the static state, the static case. Now, in our first case, what we said about the capacitor is our capacitor acts like a closed switch. Just for the brief instant when we first close the switch, it lets all the current go through. But as soon as it starts to charge, it's now pushing back against that battery. And so when it's been closed now for a very long time, then our capacitor acts like an open switch, and it will let no current through. So let's go ahead and take each of those cases. When we have at t equals 0, we've got our, what we had before, our effective resistance, which we just calculated before, was 275 ohms. That's from the previous page. And so that means that our current in the main branch happens to be 275 over and I've got 1500 volts over 275. Oops, sorry about that. That's in my face. Over 275 ohms. And that gives me about 5.4 amperes. And so if I've got 5.4 amperes across here, that means my voltage drop is going to be 5.4 times 200, or 1090 volts. Now that's my voltage drop across R1, okay? Which means if my voltage drop across R1 is, oops, if my voltage drop across R1 is 1090, and that's right here, Well, what's my voltage drop across R2? Well, guess what? These two are in parallel. And so they're going to have the same voltage across them. So we have to use our loop rule, and we're going to say 1500 minus 1090 gives me 410. And so that is now the voltage across R1. So I'm going to say R2 is 410 volts. All right, now let's go ahead and find at time goes to infinity. And so what we have is the effective resistance now. Now, in this case, what's our effective resistance? Well, guess what? This one is out of the picture. And so that means our effective resistance is going to be 200 plus 300 or 500 ohms. And that means our current is going to be 1500 volts over 500 ohms is equal to 3 amperes. And that means my voltage across R1, 3 amperes times 200 ohms is going to be 600 volts, which means that my voltage across R2 is going to be 900 volts. And so you can see that when I first close the switch, I have a very small voltage drop across here. And then when it's closed for a long time, we're increasing the resistance. Why are we increasing the resistance from 275 to 500? Because we're going from a parallel circuit to a series circuit. Because once this capacitor is charged right here, once this capacitor is charged, there's no current going through here, and I've just got this series circuit. All right, let's take it to the last one. We got one more, and then we'll throw it back to Frisco, Texas. This one shows us 2 batteries, and I really got the lucky draw tonight because Kristen did the hard one. Let's look at this one. We've got 12 volts pushing this way and 6 volts pushing this way. And I know sometimes in physics, the answer is counter obvious. It's not in this case, it's obvious. So when I push these against each other, what I actually get in actuality, in reality, is 6 volts to the right. 12 volts to the right, 6 volts to the left, gives me 6 volts to the right. And so we want to know what the resistance is in R. And so here are our resistors. Okay, this is our unknown resistor. I'm going to take away the 2 batteries, 12 and 6, and replace it with 1, 6. This is 0.2 ohms. This is 0.3 ohms. This is 1.5 ohms. And we're given that the current is 2 amps. Well, okay, let's find out. We know that I is equal to V over R, which means that R is equal to V over I. And so we've got a voltage of 6 volts, effective voltage, divided by 2 amps, which means we have a total of 3 ohms. Now, where do I get 3 ohms? Well, I have 1.5 plus 0.3 plus 0.2. So 1.5 plus 0.3 plus 0.2 gives me 2 ohms, but I need a total of 3, which means this R is 2 ohms. So not 2, I'm sorry. Let me try that again. I have 2, I need a total of 3. This R is 1 ohm. Oh my gosh. Sorry about that. A little bit of math error. We can all do it. Thank you so much for that. I think you can see it's a good problem to practice. And again, it's not about all the notes. It's not about looking up stuff. You're going to practice for mastery in this test. So we've got some more mastery for you tonight. We're going to throw it back to Kristen. Are you ready for us in Frisco?
Sure am. Okay, thanks, Roger. And also, like, being able to do that math is really, really important on those ones. And also making sure that you can put it into words, right? Like how that changing resistance affects the current and how the potential difference is changing because of those things. So it's awesome to do the math on like your scrap piece of paper or side piece of paper, but ultimately what you're going to have to do this year, what we are guessing as much as we can, and what everything has been told to us by College Board is that you are going to be explaining a lot more than you are just calculating, right? If you go back to that where we looked at those 2 questions and what kinds of questions you're going to see, it says focus on concepts, not traditional math. So you can still do math. You can still maybe use math in your words and explaining, but you got to make sure you're using your words, like I tell my 4-year-old. All right, so we've got a lab-based problem here. So we can have some practice with that since it's been a couple of days since we've done a lab problem. We have a circuit, and we have some physics students that are analyzing the circuit to the right. We have a variable DC power supply connected to an ammeter and 3 resistors. The resistances of the 2 resistors, R2 and R3, are known, which are both 50 ohms, but the 3rd resistor, R1, is unknown. So you are to describe for me an experiment that the students could do in order to determine the unknown resistance, R1. Be sure to include what measurements need to be made, not make, and with what equipment they should make the measurements. Sorry about my grammar there, guys. Okay, so I'm gonna give you a second to think about it. What would you do for an experiment that you could determine that resistance, R1? What equipment would you use? What measurements would you make? Okay, so if we're looking for resistance, what other things are we probably going to want to know? We're probably going to want to know the current, and we're probably going to want to know the potential difference, right? So the ammeter is already in there because this is a problem that I adjusted from a previous problem and rewrote, but maybe this wasn't already there, right? And you want to tell me that you are going to connect an ammeter in series with the power supply to measure current in the circuit, right? What are you measuring? We're measuring current with what are you measuring it? With the ammeter. And what else do we want to probably measure? That potential difference of the power supply. So how do we connect voltmeters in our circuit? Always in parallel. So we're going to connect a voltmeter in parallel with the power supply to measure the potential difference of the power supply. Okay, and then what you always still want to keep in mind is what variables could you change, because you always want to do multiple trials, right? We're never really going to be happy with doing something once because we don't know how valid that data is. So in order to reduce our error, we always want to take more trials. So what can we change? Well, we've got a variable power supply. So we're going to change that potential difference, and we're going to measure that and the current, right? So we're going to do multiple trials, changing the power supply potential difference. Okay, so what did we measure? With what did we measure it? And how do we do multiple trials to reduce error? When you are writing a procedure, those are the 3 things that I want you to be thinking about. Okay. Next, we want the students to create a linear graph from which R1 could be determined, right? So we want to make a nice straight line on our graph from which we could get that information. Why do we always want to make a nice straight line? Because we want to be able to use the slope to find something. So what would you want to put on your horizontal axis, and what would you want to put on your vertical axis? Well, if I know the potential difference, right? So if we make a little data table here, and I know what the, let's just say setting 1, 2, 3, 4, 5, and I know what the potential difference is across that power supply, and I know what the total current is through my circuit. Well, if I know V and I, what can I find? I can find that R. So if we use Ohm's law, okay, and my voltage and my current are my 2 variables, how would I graph those? We bring our constants on one side, variables on the other. So I would say V over I is equal to R. Okay, then I've got my nice Y over X equals slope. So V is going to be Y, current's going to be X, and that resistance is going to be the slope. But So we're going to get a nice straight line, right? So what are you going to graph on the horizontal? We're going to graph the current. And on the vertical, we're going to graph that potential difference. And then how would we use their graph to determine the unknown resistance? Okay, so I'm going to give you one more second to think about that. So my big question here for you is, what resistance is that slope equal to? We said the slope is going to be equal to R, but what resistance is it? Well, if this is the total current going through my circuit, and this is the total potential difference, and this is going to be our equivalent resistance. So the slope here, let's write it where we have a little bit more room. So this is going to be part C. The slope of our potential versus current graph is the equivalent resistance. Now I can use that though to find what that resistance is in that resistor 1 because I know what my other two resistors are. So we got to look what's in series, what's in parallel, how would we find what that R1 is? So if I look at R2 and R3, they are in series with each other, but that branch is in parallel with R1. So if we were to write an equation, the equivalent resistance is equal to, well, since they're in parallel, we have to say 1 over R1 plus 1 over R2 plus R3. Right, so again, we're not going to actually be focused on these calculations, but how would you do it? You would take that graph's slope, you would set that slope equal to the equivalent resistance, which is that equation we just found, and then you would solve for what R1 is. Okay. And then lastly, we always love to switch things up, right? So this amp meter, let's use this one that's here in series with the battery. This amp meter was found to be non-ideal. So would your calculated R1, right, the R1 that we just got from our graph, would that be less than, greater than, or equal to what our actual resistance is with this non-ideal amp meter? So again, I'll give you a couple of minutes to think about that and how you know. Okay, if you need more time, you can pause it. But we want to look at how that changes things, right? First of all, what does it mean if my amp meter is not an ideal amp meter? Remember, ideal amp meters want to have a very low resistance, right? Essentially 0, because we don't want that current to be changing due to that amp meter. If we add an amp meter that is non-ideal, then that amp meter has its own resistance. What does that do to the total resistance of my circuit? Well, if I add this in and that's in series with the battery, well, I have to add that in. And so that's really increasing what my total resistance is, which is taking away from what could have been that equivalent resistance of just this part. So let's say when we did this data and we found the slope and plugged it in, we got an equivalent resistance of 60, right? So let's say we have an equivalent resistance of 60 ohms here. So when we said that amp meter was ideal, well, that 60 ohms was just going into the equivalent resistance of those parallel branches. But now when we add that resistor in, it has its own resistance, right? Let's say that resistance is 5 ohms even if it's a low resistance. Well, that means since it's in series with the battery, well, if I want to find what the equivalent resistance of just the parallel branch is, that's really only 55 ohms. Okay, and so that means that the actual would have to be lower So the calculated one we get would be higher. So calculated for the is higher than actual. Since adding, oops, sorry, in the amp meter in series increases the resistance. Okay, so what is that going to change and how would that affect your data? There's always kind of one of those types of questions on a lab-based question. Okay, so hopefully that helps there with that lab-based question and with capacitors in circuits. So tomorrow we are going to go into putting in some capacitors and what happens not just when we close the switch or a long time after. What's that in-between stuff, right, Roger?
Yeah, I'm really, actually, I've been chomping at the bit. I want to do a differential equation, so it'll be a lot of fun. Tune in
That's the
for some
calculus
awesome
teacher.
math.
Okay, well, you guys have a great night. Thanks for watching, and we'll see you tomorrow.